There we go. So you should be able to see my slides, hopefully.
Yes, yes.
Okay.
Just 1 second. Okay, I think it started recording. So, okay, so we are very glad to have for our final APRG seminar talk of the semester, James Pascoe from the University of Florida. He will talk to us about geometric dilation and the quantum annulus. Over to you, James.
Oh, okay. So yeah, so today I'm going to talk to you about things that are related to, I guess, the von Neumann inequality and the Sz-Nagy Dilation theorem, and sort of a nice proof of those using, I guess, complex analysis and sort of the maximum principle. So sort of the point is the geometric part is going to be that we're going to sort of use complex analysis to do dilation theory. And then the quantum annulus sort of comes in because I guess the tricks that we're going to use to prove von Neumann's inequality actually work on more general domains, which people have been interested in for a little while. The other thing I should say is that, as you can tell, that I made my slides from taking another talk and then deleting everything from the previous talk except for the date, but sorry that the date's wrong. Okay. Okay, so now I'll talk about some of our basic notions just to review. I'm sure many of you have heard of these things before. I just wanted to make sure that we're sort of on the same page. So Hilbert spaces are sort of the natural generalization of Euclidean space. A Hilbert space is a complete vector space over C with an inner product. We could give a formal definition, but I don't think that would be particularly enlightening if you haven't seen one before. But the point is that the norm is sort of given by sort of the inner product of H with itself to the 1/2. And then sort of, if you haven't sort of dealt with them by hands before, the point is that you've probably encountered them before in disguise. So Cn is a Hilbert space where whenever we take V and W as vectors, really we just take component-wise the product and conjugate the Wi. The conjugate, because we're working over, I guess, a complex vector space. Secondly, I mean, the other kind of inner product that's going to show up in this talk is essentially if you have functions on a measure space, you could look at the integral of f times g bar, and that could be the inner product between f and g. And the point is that this is supposed to give us sort of the same thing that you would get for the dot product in, like, I guess, multivariable calculus. So that's about it. So then Hilbert spaces, well, generally Banach spaces have nice operators on them, but we're going to deal with operators on a Hilbert space. So if we have a Hilbert space, the set of bounded linear operators on H, we're denoting by B of H. So it's bounded operators on the Hilbert space H. That is, these are just the continuous linear maps from H to itself. So the norm of an operator is given by just, the soup over all possible norm 1 vectors of T evaluated at V. Okay, and given an operator, it has an adjoint, which you should imagine is just some infinite version, which is some, version of the conjugate transpose that you encounter in linear algebra. So the adjoint is meant to satisfy this identity. So if you take T times V, inner product with W, then that's supposed to equal to V hitting T star times W. So that's sort of the defining relation for the adjoint. This uniquely defines another bounded operator, T star, and that operator happens to have the same norm as T. So sort of your classical intuition from linear algebra. And then the final thing that we're going to need in terms of reviewing operators is a unitary is an operator which satisfies U star equals U star U equals to the identity. Note that if H is an infinite dimensional Hilbert space, you sort of need both of these relations. You need that U star is equal to U star U equals to 1. In finite dimensions, this is sort of a little bit redundant, but again, just that's sort of not so important. Okay, so now we're going to talk about von Neumann's inequality and unitary dilation. So the idea is that, first of all, we want to bound the behavior of a function at an operator by its values in the complex plane as a function of a complex variable. And then the other thing that we want to do is we want to figure out a way to model an operator, a contraction in this case, by an operator, by a unitary operator, which is in theory simpler because unitary operators are normal. So the first thing that we want to talk about is von Neumann's inequality. So this was proved by von Neumann in 51. So if I have a polynomial, and then I have T inside of the bounded operators on a Hilbert space such that it's a contraction, then if I take the norm of P of T, that's less than or equal to the sup of P of Z over the disk. So the point is that if I take my polynomial and I take its supremum, the supremum of its like absolute value or modulus over the disk, that's going to be greater than or equal to the norm of this polynomial evaluated at that operator. Okay. So that's sort of a nice fact. It's so there's also the notion of dilation. So if I have T and U bounded operators on a Hilbert space, one of them bounded operator on a Hilbert space H, one of them bounded operator on a Hilbert space K, we say that T polynomially dilates to U if there is a map P taking H to K, which is another continuous operator, such that T to the N equals to P star U to the N P for all N in the non-negative integers. So basically you want it to be the case that sort of the T to the N is a compression of U to the N for all non-negative integers N. And then we'll say that T rationally dilates to U if there is, if you have a similar situation, but instead you have that T to the N is a compression of U to the N for all N in the integers. So we wouldn't want to just include the non-negative ones. This is whenever we can include all integers. So sort of this is supposed to be, the polynomial dilation is supposed to work well with, is set up to work well with power series. You should think that the rational dilation is supposed to work well with Laurent series. So that's sort of, we'll get to rational dilation a little bit later. For the first half of the talk, we'll probably talk mostly about polynomial dilation. So the Sz-Nagy dilation theorem says that if I have, it says let P be a polynomial. I just sort of, that's not useful. Sorry, I just, okay, anyway, but let T be a bounded operator such that it's a contraction. Then there exists a Hilbert space K and an operator on that Hilbert space, which is unitary, such that T polynomially dilates to U. So basically, any contractive operator polynomially dilates to a unitary operator. So this says that contractions dilate to unitaries, which is nice. So how do we prove this Sz-Nagy dilation theorem? Well, we start out with a contraction, and then we define this defect operator dt to be 1 minus t star t. Then you write down some giant matrix S, which is an infinite matrix. So in the first column looks like T, and then your defect operator dt. In the second column, basically you're 0 in the first two slots, and then you're 1 after. Then you have 1. Then you have zeros elsewhere. And you have similar here. So then sort of it looks like this T dt and followed by a diagonal of all 1s. So let's stare at that for a moment. And so then if you look at this S, then what's nice about it is that it is an isometry. So you can sort of argue that it's an isometry either by formally evaluating this S star S or reasoning that if you hit this with a vector, you would get out a vector with the same norm. It is a little bit, I should say, there's a little bit of a dangerous bend here in saying that this operator has a square root. The reason why this operator 1 minus T star T has a square root is because it's a positive operator, a positive semi-definite operator, and we can therefore use like the functional calculus. And so there's a lot of hidden developments here encoding the fact that the square root makes sense. So finally, the desired unitary dilation is given by this concrete formula. So we take our S that we define up here, and then we form a matrix out of S, 1 minus S star, SS star, then negative S star, something like that. And the point is that if I've written down all these formulas correctly, this S turns out to be an isometry and this U turns out to be a unitary, essentially whenever S is an isometry. And so this says that, so this gives you a unitary dilation. I should note that T for S, T is a restriction of S to a co-invariant subspace. And for U, S is a restriction of U to an invariant subspace. So somehow it's the restriction to the intersection of an invariant and co-invariant subspace. So that's one way that you can sort of think about this topic. But how you come up with these algebraic relations is some sort of magical thing that happens. Okay, but if we write these down, it happens to work.
Do you know who proved it? Like who gave this proof?
I'm not sure who gave this proof. I'm not sure whether this is Sz-Nagy's original proof or not. I think Sz-Nagy uses the defect operator, but I'm not sure off the top of my head.
This Apurva, this particular proof appears in a one-page paper by someone called Schaeffer.
Cool.
Okay.
Yeah. So this is like sort of a very So I didn't. Yeah, thanks for the reference. So this is so this is just a very slick sort of algebraic proof in the sense that you write some stuff down and then it magically all works out, or somehow you get lucky. Okay, so then we can get this von Neumann inequality from the Sz-Nagy dilation by doing, well, note that if we have a unitary which dilates T, then the norm of P of T has to be less than or equal to the norm of P of U of that unitary. But then unitaries can be diagonalized by the spectral theorem. So basically the norm of a function evaluated at a unitary is just the sup over the spectrum of that function evaluated at the elements of the spectrum. And if we have a unitary, the spectrum lies in the boundary of the unit disk. And then by the maximum modulus principle, we know that that's the same as the sup of this polynomial over the whole disk as well. So yeah, so the point is that because we know that this is less than or equal to the sup of P of Z over the whole disk. You don't even need the maximum modulus principle for that, but sort of this says that so this says that P of U is less than or equal to the maximum of this P of Z. So essentially diagonalization plus this Sz-Nagy theorem prove the von Neumann inequality. And so this is very nice because it says that the von Neumann inequality has a very slick algebraic proof we might argue that having to diagonalize is a little bit of technology, but this is a very nice proof. So some algebraic calculations. So what have we learned here? So what's going on here is that some algebraic calculations, plus using a little bit of the spectral theorem, imply this Sz-Nagy Dilation theorem and the von Neumann, and from the Sz-Nagy Dilation theorem you can get this von Neumann inequality. So I should comment that a common theme in non-commutative real algebraic geometry and more broadly non-commutative function theory, so essentially the theory of non-commutative polynomials and rational functions and inequalities on their spectra, often have, so if you have a statement about something like that, those often have algebraic certificates and proofs. So these are called positive Stellensatz. So for example, Helton's to Annals paper, where he proved that a positive non-commutative polynomial is a sum of squares, which is an analog of the classic Arden-Schreier thing. Helton McCullough's proof of a non-commutative positive Stellensatz and transactions, where basically they prove an analog, they basically prove a non-commutative analog of Putnar's positive Stellensatz from the early 90s. And then I proved a rational case of that at some point. But the point is that our goal for today is going to be to look at these theorems, this Sz-Nagy theorem and the von Neumann inequality from a geometric perspective. And this geometric perspective is going to allow us to develop several generalizations where whatever the algebraic formula that we might need to write down, if one exists, is just not, is opaque or isn't just clear to us. And maybe this isn't clear to us. Maybe it took a few years for people to sort of figure this out anyway. But the point is that we want to use this. We want to sort of have some way of cooking up, dilation theorems and von Neumann inequality type statements without as much sort of having to, without just sort of having to write something down and have that be the thing that works, because it sort of might be hard to come up with that. So now I'm going to give an alternative proof of the von Neumann inequality, which is due to Nelson in the early 60s with a few bells and whistles changed, so a few minor adjustments. So first I need to review a few ingredients that are going to go into that proof. So first we have the maximum modulus principle. So the maximum modulus principle states that a complex analytic function takes its maximum modulus on the boundary. The maximum modulus principle also holds for Banach space-valued complex analytic functions, so complete norm vector space-valued analytic functions, which is the formulation that we're going to need. So some physical intuition for the maximum modulus principle comes from the fact that I guess if you take a complex analytic function, its real part is harmonic. And what do harmonic functions physically model? Well, physically, harmonic functions are supposed to correspond to the steady state of diffusion-like processes. And thus, you could imagine that you cannot have a maximum concentration at some interior point, or else that would have dissipated. So for example, imagine you've got a disk made out of metal. Imagine that it's hottest at the middle of that disk. Heat follows a diffusion, is a diffusion-like process. So if it were really hot at the middle and it's supposed to be it wouldn't be in a steady state because that heat would want to diffuse and go other places in the disk. So that's sort of a physics proof of the maximum modulus principle. Once you know that the real part of a complex analytic function is harmonic. Maybe you need to do some polarization to turn this into an actual proof, but this is sort of a nice sort of evidence for how maybe people came up with this in the first place. So The next thing is the singular value decomposition. So the singular value decomposition states that if I've got a matrix, in this case, we're going to use square matrices, but we could use rectangular matrices if we wanted to. But it's slightly more complicated to state the singular value decomposition, and that's set up. So a matrix T can be written as U star sigma V, where U and V are unitary matrices. And sigma is a diagonal matrix with the singular values on it, where the singular values are listed in decreasing order. So I want sigma 1 to be the biggest. And so these sigma I are called the singular values. And the norm of a matrix is just the maximum of these singular values. And if we've ordered them in decreasing order, this is just going to be equal to sigma 1. Okay. Where we're viewing Cn as a Hilbert space, which is what matrices, n by n matrices over C naturally act on. Okay, the next ingredient that we're going to need are automorphisms of the complex unit disk. So if I write down this function b alpha to be just z minus alpha over 1 minus alpha bar z, for alpha being some point inside of the unit disk, then these b alphas are automorphisms of the unit disk. Namely, this b alpha is a complex analytic function of z, and b alpha of 0 is negative alpha, and b alpha of e to the I theta is equal to 1. Okay, so yeah, so these are the so-called automorphisms of the unit disk. Basically, they're holomorphic maps from the unit disk to itself that are bijective. So now I'm going to give you a proof of von Neumann's inequality, which is due to Nelson. So this is what I'm going to call the automorphic Nelson's trick. So if we have a matrix T, let's say that it's contractive. Again, if we take its singular value decomposition, we could write that down as just being T equals to U star sigma V. And then we could define a matrix valued function by just putting b negative sigma 1, b negative sigma 2, b negative sigma n on the diagonal of a diagonal matrix. We'll call that sigma hat of z. Note that at 0, this is supposed to just give me this sigma, because at 0, recall that b alpha of 0 is negative alpha. So that says that whenever z is 0, then here I'm going to get sigma 1, here I'll get sigma 2, then eventually I'll get sigma n. And so then I'm going to define t hat of z to be just u star sigma hat of z v. Okay, so now for any polynomial p, this p of t hat of z takes maximum norm on the boundary of the unit disk, where this t hat is unitary, because whenever we put in e to the I theta for z, these diagonal elements here are going to be unimodular. They're going to have modulus 1. So therefore, this is unitary, and therefore a product of unitaries is unitary. So u star is unitary, sigma is unitary, and v is unitary. So therefore, well, I mean, in this case, so u star sigma hat of something in the boundary is going to be unitary, and then v. This whole thing will be unitary. And so thus we know that the sup of the norm of this quantity happens at a unitary in finite dimensions, actually. And therefore we can diagonalize it and get von Neumann's inequality. Moreover, this if I take t hat and I restrict it to t to the boundary of the unit disk, this is naturally an operator on L2 of the unit circle, tensored with Cn, or really just the direct sum of n copies of L2 of the unit circle. And this gives a unitary dilation of T. Okay, so the thing that I will mention here is that historically, instead of putting these b sigma i's on the diagonal, basically Nelson put lambda 1, lambda 2, dot, 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 up to lambda n, which then also works to give sort of a similar proof, but doesn't sort of give. So the thing that's nice about this dilation is that it's actually going to turn, this one turns out to be minimal for matrices. Whereas his is on some more complicated, sort of, I don't think that Nelson or any of the follow-ups have ever really observed that actually this technique can be used to give not only this von Neumann inequality, which is what this technique was originally adapted to do, but it also gives unitary dilations in a very natural way on very natural spaces. Okay, so what was the key here? The key here was that we took a matrix T, which was contractive. We wrote down its singular value decomposition. We replaced the singular values by functions which take the singular values at 0, but also map. And then on the boundary, they map into things with, say, modulus 1, i.e. things in the boundary of the disk. Then we defined a matrix valued function, and then used the maximum modulus principle to get von Neumann's inequality, and then actually just looked at this object that we had constructed to find a unitary dilation of our original T. Okay, so the next part of the talk, we're going to talk about what are called operator annuli. So first, I want to talk a little bit about spectral sets. So if I have k a constant greater than 1 and d a subset of C, so some other domain than maybe the unit disk, and I have T inside of the bounded operators on a Hilbert space, we're going to say that D is a K spectral set for T if for every rational function with poles off D, we have that the norm of R of T is less than or equal to this constant times the sup of the modulus of R of Z. So we say that D is a spectral set if D is a one spectral set for T. So the von Neumann inequality can be rephrased as saying that the closed unit disk is a spectral set for any contraction. So yeah, so spectral sets allow us to sort of change the problem in the sense that maybe we don't necessarily want this inequality to be true without this K here, but we're allowing sort of a little bit of a fudge factor here. Okay, so now I want to talk about, so first we're going to define the annulus with parameter R to be the set of complex numbers where Z is between R and 1 over R, where R is some number that's bigger than 1. And we're going to call, so this essentially looks like a donut. So you've got a little circle inside and then a big circle outside. The angular annulus consists of all operators, or we could say angular annulus or spectral annulus consists of all operators T, such that this annulus with radius R is a spectral set for T. And then we're going to define the quantum annulus to be the set of all operators such that the norm of T is less than R and the norm of T inverse is also less than R. Okay, and implicitly we're insisting that the operators inside of this quantum annulus be invertible. Okay. So Asler in 1985 showed that an operator T rationally dilates to a normal operator with spectrum in the boundary of the annulus. So on the sort of two rings bounding our donut, if and only if T is in the Asler annulus. So what I should say is that there are operators inside of this quantum annulus which are not in this angular annulus. So this sort of says that rational dilation holds for operators in this Agler annulus. The other thing that I should say is that for the quantum annulus, this annulus AR is known to be a 1 plus square root 2 spectral set. And we know that no constant, so it's a 1 plus square root 2 spectral set, which is a result due to Crouzet and Greenbaum. But this AR is a spectral set for this quantum annulus. And we know that the constant has to be constant K in the definition of spectral, in definition of K spectral set here, it has to be at least 2 in the case of the quantum annulus to use this annulus as a spectral set. Okay, so I should note that the analog of this Agler's theorem saying that operators which have the annulus as a spectral set have boundary dilations. That fails for triply connected domains. So that was proven by, I guess, Dritchell and McCullough, and around the same time by Agler, Harland, and Raphael in Memoirs. So this was sort of shocking result in the sense that it fails for domains that have more holes. And there's sort of some deep geometric reasons for this that have, which are sort of interesting. So recently, me and Scott McCullough sort of got interested in the problem of, well, what do operators in the quantum annulus dilate to? So we know that contractions dilate to unitaries. We know that things that have the annulus as a spectral set dilate to things with spectrum in the boundary, normal operators with spectrum in the boundary of the annulus. So we were trying to figure out what do operators that are in the quantum annulus dilate to. So what we figured out was that operators in this quantum annulus rationally dilate to operators of the form U times a block matrix, which looks like R and 1 over R. So they almost look like something with look like a normal operator with spectrum in the boundary of the annulus. But the problem is that this U can mix up this block that has the R part and the 1 over R part, because U need not be block diagonal. So sort of the case for the annulus being a spectral set corresponded to exactly to when U was block diagonal with respect to this diagonal decomposition. Okay, so let's talk about how we would do Nelson's trick for this quantum annulus. So if I have T inside of the n by n matrices over C intersect the quantum annulus, and we let T have singular decomposition as U star sigma V, one can note that the singular values actually have to lie inside of the annulus with radius R. And so then what we're going to do is, instead of using those automorphisms of the unit disk, we're going to use covering maps of from the disk into the annulus with radius R. So, which takes the value alpha at 0. So the point is that for any alpha inside of this annulus, there's a map taking the disk to AR, which takes alpha to 0 and takes the boundary of the disk to the boundary of this annulus almost everywhere except for 2 points. One way that you can see this is you could send the disk to a vertical strip, and then you could apply the exponential to that vertical strip, and you would get a map that covers this annulus. In some sense, this covering map is, once you specify this value alpha, is essentially unique. So now let's define our sigma hat just to be, well, I put those covering maps on the diagonal. And then I let t hat of z be just u star sigma hat of z in v. And then naturally, this t hat restricted to t is an operator on L2 of the circle, tensored with Cn. And that gives the desired dilation because on the boundary, this function takes values which are matrices with singular values, either r or 1 over r. And so then we can view this as some sort of direct integral. We can view this t hat of z as an operator on this as sort of a direct integral of the operators for each z equals e to the I theta. And those operators have singular values r and 1 over r. So this argument, if we go back to look at Nelson's trick, is essentially the same thing. So basically we have some nice complex analytic maps here, and then we get out some sort of dilation theorem. We don't really have a nice analog of the von Neumann inequality here, and that's because there's a gap between this Algebraic annulus and the quantum annulus, in the sense that for elements of the quantum annulus, we only know that the annulus is a 1 plus square root 2 spectral set, and we know that it's not actually a spectral set. So there are elements inside of this quantum annulus which are not in this Algebraic annulus. Okay. One can imagine that our dilation theorem could be used to help compute that spectral constant more exactly, because we only have an estimate that says that it's at most 1 plus square root of 2 for sort of the best possible k there. But the we know that the maximum has to be attained at an operator of this form, and then we also know that the function that it attains its maximum at has to be an inner function, which is also special. So the point is that you know that these are sort of the candidate operators, and we know that the candidate functions are inner functions because I guess the convex hull of the inner functions on the annulus is equal to the space of all functions on the annulus. Okay, so now I want to talk about other matters, other places where maybe we can apply this trick. So we can also apply Nelson's trick to tuples of doubly, or sorry, I miswrote this, but this Nelson's trick to doubly commuting tuples of contractive matrices. So that means that not only does Ti commute with Tj, but Ti needs to commute with Tj star whenever I does not equal to j. So that basically makes it so that then the U's and the V's that occur in their SVDs happen to commute. And so then that makes it very suitable for this Nelson's trick. We also have row contractions, and thus we recover like this non-commutative multivariate dilation theory that essentially this Bunce-Frajo-Popescu non-commutative dilation theory. And then we could also do like a row version of the quantum annulus by sort of, and for this row contraction case and this row quantum annulus, we would need to apply Nelson's trick using a singular value decomposition that's not square, but everything's still going to go through. You're just going to get some sort of like isometric dilation rather than a proper unitary one. So an important question is whether or not this trick can be applied to pairs of commuting contractive matrices. Sort of get to why we think that might work or might not work. So a classical theorem due to Ando was that if you have a polynomial in 2 variables and we let T1 and T2 be in B of H such that they're both contractions and T1 and T2 commute, then P of T1, T2 is less than or equal to the sup over the unit disk of this polynomial. Okay, so basically, this is a two-variable analog of Ando's inequality. So if you have pairs of commuting matrices, then it's the case that the norm of this has to be less than or equal to the norm over the bidisk. So it's sort of interesting that Ando's inequality fails for commuting triples, and therefore it fails for basically anything more than two commuting operators. And you can just find rinky-dink examples. So the point is that Parrott in the 1970s and Parrott and Veropoulos found concrete counterexamples to the natural three variable analog of Ando's inequality. And this also, in turn, because I guess one of the things that's going on in the background here is that people often use von Neumann's inequality to develop complex analytic ideas. This says that sort of two complex variables happens to be a little bit nicer than three or more complex variables for specific domains like the bidisk. So the tridisk is somehow much worse than the bidisk in terms of understanding complex analytic function theory. Okay, so here's another result, which is sort of interesting, that holds for two variables, which is sort of interesting. So if I take the algebra generated by a commuting pair of n by n matrices, that algebra is at most n-dimensional. Okay, so the algebra generated by a commuting pair of n by n matrices is at most n-dimensional. And the reason for this is that if you look at the set of pairs of commuting matrices as a variety, that variety is irreducible and diagonalizable elements are dense. So then, and for diagonalizable elements, for simultaneously diagonalizable pairs, this result is obvious. Problem. So it's known that for four tuples of commuting matrices, the above theorem fails. So they can have, if I have four commuting matrices, the algebra that they generate can be bigger than n-dimensional. And then the variety of commuting pairs in two variables is, has this diagonalizable elements being dense, and for diagonalizable elements, the result's obvious, and then some sort of semi-continuity of the rank. I forget if it's upper or lower semi-continuity, but one of the two. But what we know is that for triples of commuting matrices, for large dimensions, it's known not to be the case that that the variety is irreducible. It's known that the variety is reducible for large sizes. And so this is sort of suggestive, because what did we do way back here? Well, let's say for this example, what did we do? Well, so what we did was we defined a function which was a function of z, which was an analytic function. And then we had this we defined this function, and then that was supposed to sort of stay inside of our nice set of operators that we care about, and then sort of be the most extreme operators on the boundary. Well, if we tried to do this for three variables, there might be two different components. And then the point is that whatever that function is going to be stuck in whatever component it started in, which is a little disturbing, because if it's stuck in one of the, so the speculation would be that for whenever the case the variety has multiple components, that only one of the components is going to have unitaries in sort of its distinguished boundary, in the place where it attains its maximum modulus. So to summarize that, so it would be really nice to have a proof of Ando's inequality that uses this Nelson's trick. We don't have that. And it would be nice to have a way to use this Nelson's trick to prove that Ando's inequality can't possibly hold in 3 or more variables because of the failure of irreducibility of the variety in large dimensions of commuting triples and matrices. So here's my conjectural speculation. So we conjecture, so there should be a Nelson's trick type argument in 2 variables. It's going to have to be complicated, but it would also maybe give, the point is like, one thing that would be nice to have just generally would be to have a slick proof of Ando's inequality. That's because typically a lot of the proofs go by first you dilate one operator, then you dilate the other operator, and sort of have to solve some key equation at some point that means that sort of the argument could have only worked in 2 variables. But it would be nice to have some sort of like complex analysis proof of Ando's inequality, first of all. And then second of all, there should be some way to use the fact that this argument can't work in 3 variables because you're going to sort of get stuck in one of the components, and it's likely that one of the components isn't going to get have unitaries in its entire distinguished boundary, the places where the maximum modulus holds. So in turn, that failure of irreducibility should imply that the distinguished boundary, or the place where the functions are forced to take their maximum, contains non-unitary points in 3 or more variables, which then would sort of, with probably a little bit of finessing, could be used to then get a proof of Ando's. Well, could you get a proof of the failure of Ando's inequality? So it'd be nice to have a geometric reason for that, because it's not clear. Like, it's clear that Ando's inequality fails in 3 or more variables and that it holds in 2 variables because you can look at the proof and understand the proof, but it's not clear like why those proofs work. It's sort of a little bit mysterious, to me at least. So I'd like to thank you for your time and attention. So thanks a lot for inviting me to give a talk. And yeah, sorry that I'm sort of half awake right now. So.
Well, thank you. Sorry, I don't know if we're half awake, but this was a wonderful talk. So thank you very much, James, for a very, very clear and very clear talk. Yeah. Are there, sorry, are there any questions? Or comments?
James?
Hello?
Hello. Now you took T invertible, then there is a part of disk around 0, which is also a part of the resolvent. So resolvent has a various components. Do you not make use of that?
I don't think so. So yeah, I don't think so. So yeah, so I don't think so.
Any further questions or comments? Okay, if there are, then let's thank the speaker for now again. And so
thanks,
that
everybody.
Wonderful.
Yeah,
Wonderful.
So I think that concludes our talk for the seminar itself for this semester, and we will meet in January next with Peter Semrel opening the semester. Let me stop the recording first.
Yeah, now I'm gonna